Okay, so let's implement shell sort. I've created a project. I'm using package academy.learnprogramming.shellsort. I've added the usual int array, the code for printing out the array, and we don't need the swap method for this because insertion sort doesn't use swap, and this is just essentially a variation on insertion sort. So let's go. So the first loop we're going to have is the one that's going to initialize the gap value that we're using and then reduce it on each iteration. So we'll say for int gap equals int array dot length over 2, because remember we're going to start with int array, a gap of int array dot length over 2, which for this array will be 7 over 2, which is 3. And then we're going to keep going as long as the gap is greater than 0, because if the gap is 0, then that means that we're going to be comparing elements against themselves. So we need a gap of 1 for the final iteration. Remember, for shell sort, the final iteration always has to have a gap of 1 because we want the final iteration to essentially be insertion sort. And on each iteration, we're going to divide the gap value by 2. And so on the first iteration, our gap value will be 7 over 2, which is 3. On the second iteration, it'll be 3 over 2, which is 1. So the second iteration will be essentially an insertion sort. So now we're going to code the actual comparing and shifting, and as you'll see, and I'll show you this afterwards, that what we're going to code here is essentially insertion sort. It's going to look slightly different because it's using gap, but it's essentially insertion sort, and we'll compare the two implementations, the two sets of code, in a minute. So I'm going to say for int I equals gap, I less than int array dot length, because we're going to want to look at all the elements in the array, I plus plus, and we're going to start out as we did with insertion sort. We're going to assign a new element field with int array I. Int array I is the value that we're going to be looking at. So that's essentially int array gap. And we're going to use j to do the traversing. So we're going to say while j is greater than equal to the gap, because if j becomes less than the gap, that means that we've hit the front of the array. And int array j minus gap is greater than new element. Well, what do we want to do? We want to shift the element at int array j minus gap up gap positions. So we're going to say int array j equals int array j minus gap. And so what we're saying here, if we were doing we're starting out with a gap of 3, so we're starting at 7, just as we did with the slides. And in the first iteration, we're going to compare 7 to j minus gap, right? Because we're going to assign 7 to new element. J is going to start at 3, and we're going to say if int array j minus gap, well, our gap for the first iteration is 3. So if int array 0, which is 20, is greater than 7, which it is, then we want to shift 7 up 3 positions. So we're going to assign int array j, which is 3. So int array 3 with int array 3 minus 3, which is int array 0. So we're essentially going to take what's at position 0 and assign it into position 3. And then once we've done that, we want to subtract the gap from j, because we're saying that now we're going to want to compare new element with whatever comes 3 positions over. Well, we've hit the front of the array at this point. We'll loop around and we'll say, well, j has to be greater than or equal to the gap, and it isn't, because at this point it's 0. And that's because there's no elements to the right here. So first we want to compare 7 against 20. If we could, we'd then compare 7 against whatever occurs 3 places in front of 20, but there is nothing. And so we're going to drop out here. And what do we want to do at this point? Just like with insertion sort, well, we're basically saying we found the insertion point for 7 when we drop out. And so we're going to assign int array j with new element. And this should look somewhat familiar because this is essentially what we were doing with insertion sort. And so after we've done that, we'd loop back around to this loop, and I would become 4. So it would become 55, J would become 4, and then what would happen is it's going to compare 55 against 35, and it's not going to do anything because 55 is greater than 35. And at that point, once again, it's going to want to jump ahead 3 places, and there's nothing, so we're going to just loop around. I will become 5, so it's going to compare 1 against minus 15, and because 1 is greater than minus 15, it's not going to do anything. It's going to loop around, and once again, it's going to want to compare to whatever's 3 spaces over, and there isn't anything, so we're going to loop back. I will become 6, so minus 22. We're going to compare minus 22 against whatever's here. Now, it's not 7 anymore, it's 20, because we moved 20 here. Minus 22 is less than 20, so we're going to shift 20 here. And then we're going to compare minus 22 to whatever's 3 spaces over. And this time we do have something 3 positions over. We actually have 7 here because on the very first iteration, we move 7 to the front. Minus 22 is less than 7. So we'll shift 7 back to where it originally was. And then at this point, it's going to want to compare 3 spaces over and there isn't anything. We've hit the front of the array, and so we'll assign minus 22 here. And at that point, we'll loop around. I will become 7, and it'll fail this condition. And so we'll drop out, loop back around to the gap loop, reduce the gap to 1, and at this point, when we enter this code, we're essentially doing an insertion sort. And so that's how shell sort optimizes insertion sort. So let's run this to make sure it's working. And we get the usual minus 22, minus 15, 1, 7, 20, 35, and 55. So let's go out to a couple of slides for a minute to compare the code for insertion sort with the code for shell sort. Okay, so here's the code that we wrote for insertion sort, and we can see that here we're starting with the first unsorted index as 1. We assign new element with whatever's at that value. We have I, and then of course we loop through all the elements to the end of the array, and if possible, we shift elements to the right. And if we drop out of this loop, then we have found the insertion position for new element. So we assign new element to I. Here's shell sort. And if you ignore this part for a minute, you'll see that this code is pretty much the same. The only difference is instead of using 1, we're using whatever the gap value is. So in the first iteration, we're going to use 3. And once again, if we go back to insertion sort, we're going to assign int array first unsorted index to new element. While in shell sort, we assign whatever's at I, the gap value, to new element. We assign I to j. It's pretty similar to what we're doing here, except the loop is taking care of assigning I. Here we need a different index because we don't want to be changing I as we traverse not the sorted partition, but the part of the array that we're looking for an insertion position for. And then we say in shell sort, while j is greater or equal to gap, and int array j minus gap is greater than new element, as long as that's true, we're going to shift the element that we're comparing against. We're going to shift it up the array by gap positions, and then we need to decrease the position of the next element that we look at by the gap, because we always want to be looking at the element that's gap positions away. And this is very similar to what we're doing here. We're saying the same thing. As long as we haven't hit the front, and this is saying as long as we haven't hit the front, and as long as the element we're looking at for shell sort, it's not really the sorted partition, but the element we're looking at that's gap positions away is greater than new element. And back in insertion sort, as long as the element we're looking at is greater than new element, we want to do the shifting. And here we want to do the shifting. And here, because we're using a gap, we have to calculate the next index we want to look at differently. We can't just decrement it by 1 as we are with insertion sort, because we're assuming a gap of 1 here. And then when we drop out of this loop, we assign new element to int array I. And here, when we drop out of the loop, we assign new element to int array j. So I think if you take a look at these two sets of code, here's insertion sort again, and here's shell sort, you can see that we're doing the same thing inside here as we're doing with insertion sort. It's just that we're examining elements that are farther away, except on the final iteration. On the final iteration, when the gap is 1, what we're doing in here is exactly the same thing as what we're doing in here. And so the final iteration, when the gap is 1, we're essentially doing an insertion sort. And that's what shell sort does. But of course, with shell sort, in the final iteration, we've already moved several of the elements closer to their sorted positions. And so there's going to be a lot less shifting that has to take place. And that's how shell sort improves on the insertion sort algorithm. And as I mentioned, you can also use the same idea to improve on bubble sort. You do some preliminary work. So instead of examining neighbors and swapping them, you'll examine elements that are further apart and swap them if necessary. And so by the time you get down to the bubble sort where you're using a gap of 1, there'll be a lot less swapping to do. So that shell sort, that's what the shell sort algorithm does for insertion sort, and it can also do it for bubble sort. I'll see you in the next video.